We have seen the measurement theory in quantum mechanics and also how to calculate probabilities. Okay, now we'll illustrate some of these things with the spin half systems. All right, especially we know, for example, we have discussed the Stern-Gerlach experiment. We know what the experimental outcomes are. All right, we have discussed sequential Stern-Gerlach experiments, etc. We know what are the possible experimental outcomes. So using this experimental outcomes, using the knowledge of the experimental outcomes of the Stern-Gerlach experiment, as well as the measurement theory and probabilities that we discussed in the last class, we'll try to build up the spin eigenkets as well as the spin operators. All right, that's what we'll be doing in this class. So this is an elaborate example just to show how these things actually work in theory. Okay. Now, before proceeding with the general discussion of observables, we once again consider spin half systems. The spin half systems are the simplest systems that we can imagine in quantum mechanics. All right, this is the simplest system in quantum mechanics. The reason is that we have seen from the experiments that if you measure the spin of an electron along any direction, right, there are only two possible measurement outcomes. You either get plus h bar by 2 or you get minus h bar by 2. Right, this is an experimental fact. This is something that we see in experiments. Okay, so we see that there are only two measurement outcomes. So based on the theory that we are developing, if there are two measurement outcomes, then the vector space or the ket space that we construct is two-dimensional, will be two-dimensional. So we are talking, if you are talking only about spin, you are talking about a two-dimensional vector space, and things cannot get any simpler. Right? So this is the reason why we give examples again and again and again from the spin half systems. So what are we going to show here? We show that the results of sequential Stern-Gerlach experiments. So we have got the experimental results on the one hand. Okay, the results when combined with the postulates of quantum mechanics. All right. So the measurement theory, for example, measurement theory plus the probability. All right, the calculation of probability postulate. Let me call it as probability postulate. Okay, now combining these two, right, combining these two, we can determine the Sx eigenkets and Sy eigenkets. All right, we can also determine the operators Sx and Sy themselves. So let's look at these eigenkets and these operators, and we'll discuss some of the properties of these eigenkets and operators. Okay, so let's go back to the sequential Stern-Gerlach experiments which we had discussed. We recall that when the Sx plus beam is subjected to an apparatus of type SGZ hat. Right? So what is this Sx plus beam? The idea is that we have got an Sx plus beam. How do you filter out an Sx plus beam? You send, what do you say? You send this beam of atoms, this beam of silver atoms into an apparatus of the type SGX hat. Okay, there are two outcomes. If you remember this, there is an outcome corresponding to plus h bar by 2 and minus h bar by 2. All right, so we can call this as Sx plus beam and this as Sx minus beam. Now we block this. All right, so if we block this, we have got an Sx plus beam. What we do next here is we send it to an SGZ hat apparatus. Right, we send it to an SGZ hat apparatus. All right, and we see that there are two outcomes. This is an experimental fact. All right, think of this as an experimental fact. This is something we observe. There are two outcomes, one characterized by SZ plus and the other one by SZ minus. All right, or plus h bar by 2 along z axis and minus h bar by 2 along z axis. Right, so the beam splits with two components with equal intensities. So experiments show that the intensities of both these beams are the same. Right? The intensities means this. So if you are sending a large number of silver atoms prepared in this manner in the Sx plus beam, right, exactly half of them, right, if you are sending a large number of them, exactly half of them will return a value plus h bar by 2 for the spin along z direction, and the other half of the atoms will return minus h bar by 2. Right, so the number of atoms in the end of the experiments, the number of atoms that measure plus h bar by 2 along z axis will be equal to a number of atoms that measure minus h bar by 2 along z axis. Right, so this means, in the language of probabilities, this means that the experimentally measured probability. The experimental measured probabilities for measuring plus h bar by 2 and minus h bar by 2 are exactly the same. Right? So there are two possibilities. The probability for measuring plus h bar by 2 along the z direction is 1 by 2, and the probability of measuring minus h bar by 2 along z axis is also 1 by 2. Okay, so this you should think of as an experimentally measured probability. So by repeating this experiment a large number of times, and we measure the number of times we get h bar by 2, and we measure the number of times we get minus h bar by 2, right? So you have to do this for what is with a large number of atoms, right? Then you calculate n1 divided by total number of atoms and n2 divided by total number of atoms in such a way that this capital N is very large, right? And we see that as n becomes larger, right, we should say this approaches half, this also approaches half. So this is how we measure the probabilities experimentally. The probability for measuring plus h bar by 2 is experimentally half, and the probability for measuring minus h bar by 2 is experimentally half. Right? Now this is the experimental side. This is the experimental fact. Okay. Now what does this mean? Right? So according to the theory that we have been developing, this means that a beam characterized by Sx plus, right, a beam characterized by Sx plus has components along both Sz plus direction, right, has components along both Sz plus direction as well as along Sz minus direction. This is the reason, according to the theory, that we get half of the times plus h bar by 2, and the other half of the times we get minus h bar by 2. Okay, so according to theory, this means that ket Sx plus, or the state characterized by Sx plus, has components along both Sz plus as well as Sz minus directions. Okay, this means again that you can actually write ket Sx plus as a linear combination of Sz plus and Sz minus. It's a linear combination of Sz plus and Sz minus. Right? Okay, now we will be using these kets quite a lot. So we'll use a simplified notation for this. For Sz plus alone, right? For Sz plus, we'll denote it as simply ket plus. Similarly, for Sz minus, we'll denote it as ket minus. All right. So this means that, let me write it in this shorthand notation here. This means that I can write ket Sx plus as C1 ket plus C2 ket minus. All right. Okay. Now we said that the measured probability. Okay, we just saw that the measured probability that the state Sx plus goes or changes to ket plus under a measurement of Sz. All right. This probability is measured to be half. Right. Similarly, the probability that ket Sx plus under a measurement of Sz changes to a state ket minus, this is also measured to be half. Right? Now this is the measured probability, but quantum mechanics gives us a rule to to calculate these probabilities. What's the rule? If the state is normalized, the probability, quantum mechanics says that, or the theory that we discussed says that, or the postulate, we postulated that this probability is actually Sx plus. So we postulated that the probability that it changes to ket plus is modulus C1 square, right? It's modulus C1 square. Or let's write it more precisely. Okay, the probability that Sx plus changes to ket plus under a measurement of Sz is actually equal to, this is equal to, so in order to calculate this, you have to take the component of Sx plus along ket plus and then find the modulus square of this, right? And then find the modulus square of this. So in other words, this is equal to modulus C1 square. All right. Similarly, the probability that Sx plus changes under a measurement of Sz changes to a ket minus. All right. This probability is given by, in order to find this probability, what do you have to do? You have to find the component of Sx plus, right? The component of Sx plus along the ket minus direction, and then you have to calculate, then you have to find the modulus square. Okay, so the probability postulate tells us that this is how we have to calculate the probabilities. Right? Now, what do we have now? This means that we must have the modulus square of this equal to 1 by 2. We also must have the modulus square of this thing is equal to 1 by 2. Okay, this 1 by 2 we got from the experimental results. So the right hand side comes from the experiments, the left hand side is from the probability postulate. Okay, now if you don't remember the probability postulate, just go back to previous classes and revise it. Right? The probability postulate says that if I have a state, right? If I have any state get alpha, let me just revise it here. If I have any state get alpha, right? The probability that this reduces to a state, let's say get a prime. Okay, under a measurement of a is given by bra a prime get alpha modulus square. Right, that's exactly what I have done here. Instead of this observable a, I have here the sz operator. Right, the sz operator. This means that the observable here is the z component of spin. So what I'm measuring here is the z component of spin. Right, and instead of get a prime, I have get plus here. Right, get plus and get minus here. Instead of get a prime, I have get plus here. Instead of get a prime here, I have got get minus here. So this is the rule that we are using. Okay, I hope this part is clear. All right. Okay. Now let's see what we can do with this. All right. Let's see what we can do with this. What does this mean? We make some space first. So by combining the probability postulate with the experimental result, we have these equations. All right. The modulus square of Sx plus, okay, the modulus square of this combination, okay, bra plus get Sx plus, this is equal to 1 by 2. 1 by 2 is measured experimentally. This is the theoretical prediction. All right. We also have this modulus square of modulus square of bra minus get Sx plus. All right. The modulus square, this is the theoretically predicted probabilities or according to probability postulate, and the measured probability is 1 by 2. These are the equations we have. So the idea is that from these equations I can determine the coefficients. We can determine bra plus ket Sx plus as well as bra minus ket Sx plus. Okay, or we can determine the component of Sx plus along ket plus, and we can determine the component of Sx plus along ket minus. Okay, in other words, if I write this Sx plus state like this, C1 ket plus C2 ket minus, right? These equations means that modulus C1 square is 1 by 2 and modulus C2 square is also 1 by 2. So from here we can find modulus C1 square and modulus C2 square. So from here we can find C1 and C2, and then we can write ket Sx plus as a linear combination of ket plus and ket minus. All right. So instead of C1, right, this is actually C1 and this is actually C2. So let's find C1 and C2. Let's find C1 and C2. Okay. So we have got modulus C1 square. What is C1? C1 is bra plus ket Sx plus. What is C2? C2 is bra minus ket Sx plus. Okay. So modulus C1 square is 1 by 2. Modulus C1 square is actually 1 by 2. What does this mean? This means that C1 is equal to 1 divided by root 2. But that's not all. Alright. Why? Because we said that this C1, C2, etc. are complex numbers. Okay. So what we need is a complex number which when you take modulus square gives you 1 by 2. It could be 1 by root 2. Right? But there could also be a pure phase here. Right? Why? Because even if there's a pure phase here, modulus C1 square, this is equal to C1 star C1 will be equal to 1 by root 2 e raised to minus I phi 1 multiplied by 1 by root 2 e raised to plus I phi 1. Because when I take a modulus square of this, it gives you e raised to minus I phi 1. And this term would just cancel. It would just give you 1. And you would get 1 by 2. Right? So you would get 1 by 2. You would get modulus C1 square equal to 1 by 2 if C1 is 1 by root 2, or even if there's a pure phase factor here, if there's a pure phase here. All right. So let's write in general C1 is equal to 1 by root 2 e raised to I phi 1. Okay. Similarly, C2, we know that modulus C2 square, this is modulus C2 square. Modulus C2 square is also 1 by 2. So this means that this is equal to 1 by root 2. Again, there could be an arbitrary phase factor here. All right. There could be a phase factor here. Right? Because any arbitrary phase factor put here would give you the same result. All right. So this equation actually, or mod C1 square equal to 1 by 2 and modulus C2 square equal to 1 by 2, actually allows us to calculate C1 and C2 only up to a phase factor. It allows us to calculate C1 and C2 only up to a phase factor. Okay. This means that now I can write Sx plus as 1 by root 2 e raised to I phi 1 ket plus 1 by root 2 e raised to minus I phi 2 ket minus. Okay. All right. Now I can do something more here actually. Right? So we have said that this ket, we have talked about this ket Sx plus. Okay, we can take it as normalized. Okay. Now the normalization does not change even if I multiply by a phase factor here. All right. The normalization does not change, or the probabilities do not change even if I multiply by a phase factor here. All right. For example, if Sx plus bar Sx plus ket Sx plus is equal to 1, all right. This means that I can find another ket which is e raised to I phi multiplied by ket Sx plus. Okay. If this is normalized, all right, if ket Sx plus is normalized to 1, then e raised to I phi ket Sx plus is also normalized to 1. All right? Because when I take the corresponding bar, this e raised to I phi will become e raised to minus I phi, and when I find the bracket, this e raised to I phi and e raised to minus I phi together will give you just 1. Okay, so the normalization does not change even if I have a pure phase factor here. So this pure phase factor here doesn't affect our probabilities. All right, so we could redefine this state here and by simply multiplying a pure phase factor. So what we can do is that we can divide throughout by e raised to I phi 1. For example, we could divide throughout by e raised to I phi 1, and the resultant state we can again call ket Sx plus. Or the resultant state we can also, or we can relabel it as ket Sx plus. Okay, so we can multiply this by e raised to minus I phi 1 on both sides, and the resultant state again I can call ket Sx plus, because it represents the same physical system. All right, and the probabilities do not change. The normalization does not change. Okay, I can absorb, in other words, I can absorb a pure phase factor into this ket without changing anything. All right, so I choose to absorb what is a pure phase factor e raised to minus I phi 1 on both sides. This means that Sx plus can now be written as 1 by root. I am multiplying by e raised to minus I phi 1. So e raised to I phi 1 minus I phi 1 multiplied by e raised to I phi 1 will become 1. Okay. So I simply will have 1 by root 2 ket plus, and here I will have e raised to minus I phi 1 multiplied by e raised to I phi 2. Okay, so that can be written as e raised to I phi 2 minus phi 1. Right, but this phi 2 minus phi 1 you could call as some other some other phase factor. Okay, so this phi 2 minus phi 1 can be now termed as, let's call it as delta 1. Okay, and you can write this as 1 by root 2 ket plus 1 by root 2 e raised to I delta 1 ket minus. Okay, I hope this is clear. So we have actually used this freedom of multiplying by a pure phase factor without changing the state or the probability. So right, we have used this freedom, and we have chosen that C1, right, the expansion coefficient is C1 is real and positive. Right, we have made a choice to make this C1 real and positive. Right, we have made use of the freedom. Okay, so this is what we get here. Let me just explain what we have here. All right. I hope this is clear. All right. So what I have done is that I have chosen to include the phase factor only in the second term. Right. I have chosen to include a phase factor only in the second term. Okay. So for this I can use the freedom that is there. So this is what we have done. Let me just what do you say? Repeat what we have done. Right. Briefly this time. Okay. So This means that, right, so we saw that the probabilities, measured probabilities are 1. This means that the component of ket Sx plus along the ket plus direction, not the component, the modulus of that component, all right, as well as the modulus of the component of Sx plus along ket minus, both these are 1 by root 2, because the square, if the modulus is 1 by root 2, this means that the square will give you 1 by 2, which are the measured probabilities, right? But the modulus is 1 by root 2 means that there could be a pure phase factor. There could be a pure phase factor. What do you mean by modulus of a complex number? These are numbers, all right? What do you mean by a modulus of a complex number? This is actually square root of z star, all right? Okay. So even if I include a pure phase factor instead of z, if I put e raised to I phi z, modulus of z wouldn't change, right? Modulus of z wouldn't change, all right? So there could be an arbitrary phase factor when I find the component of Sx plus along ket plus as well as the component of Sx plus along ket minus. There could be a phase factor. All right. Now, using the freedoms that are available here, I choose to write the phase factor only in the second term. Right, only in the second term. Now, if there is a phase factor in the first term, we can divide throughout by that phase factor without changing the state or the probabilities. We can divide throughout by this phase factor that appears here, and then you can choose not to write a phase factor for the first term. Okay, so delta 1 here is real. So in writing 1, we have used the fact that the overall phase common to both ket plus and ket minus of a state ket is immaterial. Okay, so the overall phase is immaterial, which means that you are allowed to multiply these things with an overall phase without changing anything at all. Okay, so this is immaterial. The coefficient of ket plus can be chosen to be real and positive by convention. So this is a convention that we are making use of. Right? We are choosing a convention. We are choosing the coefficient of ket plus in ket Sx plus. Okay, in the expansion of ket Sx plus, we are choosing the coefficient of ket plus to be real and positive. And how do we make this choice? By using the fact that the overall phase of a state ket is immaterial. Right? So if you have ket alpha, right, you could also simply multiply this by a pure phase factor without changing anything at all. It does not change the state, it does not change the probabilities. Okay, so you have a freedom to multiply this by pure phase factor. This is exactly what we have used here to choose the coefficient of ket plus as real and positive. Okay, I hope this is clear. So by comparing the probability postulate with the experimentally measured probabilities, we find that we can write ket Sx plus as a linear combination of ket plus and ket minus with coefficients appearing here, with expansion coefficients appearing in this form. Expansion coefficients are 1 by root 2 and 1 by root 2 e raised to I delta 1. Okay. So what we have is, we have got the expression for ket Sx plus as a linear combination of ket plus and ket minus. Okay, this linear combination that we wrote down was 1 by root 2 ket plus 1 by root 2 e raised to I delta 1 ket minus. All right. Okay, now we need to find a similar expression for ket Sx minus. So that's our next aim. Now how do we do this? Right? Now again, we look at the experiments and we find that if I have a beam of atoms characterized by Sx plus, right, and I send it to an SGX hat apparatus. In other words, I am measuring the x component of spin of a beam of atoms characterized by Sx plus. Right, and what I see is that I always get plus h bar by 2. I always get plus h bar by 2 and never minus h bar by 2 and never minus h bar by 2. This means that if I take, this means that in the language of probabilities, this means that if I take a beam, if I take a ket Sx plus, right, and I measure Sx on it, the x component of spin on it, right, the probability that it changes to or it remains in the state Sx plus, this is equal to 1, and the probability that ket Sx plus on the measurement of Sx gives Sx minus, this probability is 0. Right? So when I say that when I am looking at the probability that ket Sx plus goes to ket Sx minus after measurement of Sx, this means that I'm looking for the probability of measuring minus h bar by 2. Right? So this is 0. What does this mean? This means that Sx plus has no component along the direction Sx minus. In other words, I can write it like this. Bra Sx minus ket Sx plus has to be equal to 0, right? Because the modulus square is 0 according to this. The probability is 0, the modulus square of this is 0, or we say that this is equal to 0, right? In other words, we can say that Sx plus alternative and Sx minus alternative are mutually exclusive, and mutually exclusive alternatives correspond to orthogonal states. Okay, we have discussed this before. Mutually exclusive alternatives correspond to orthogonal kets. Alright, this means that we have a condition. We have got a condition here. The condition is that the component of Sx plus along the direction Sx minus is equal to 0. Okay, this we can find experimentally and comparing it with our theory. Experimentally, we see that the probability is 0 whenever you have a set of atoms, a beam of atoms characterized by Sx plus, and you measure Sx on it, you always get plus h bar by 2, never anything else. Now that fact can be written in this form. The component of Sx plus along Sx minus direction is 0. Alright. So we don't know Sx minus, but what we need is that we need to write it as a linear combination of ket plus and ket minus. Alright. This means that what I need is an expression for Sx minus of the form A ket plus plus B ket minus. All right, now I make use of this relation. This means that bra Sx minus can be written as, all right, this is ket Sx minus, so bra Sx minus can be written as A star bra plus B star bra minus. Okay, and ket Sx plus is already given here, so let me make the multiplication. Sx minus bra Sx minus ket Sx plus is equal to 0. This is what I demand. This means that A star bar plus B star bar minus multiplied by 1 by root 2 ket plus 1 by root 2 e raised to I delta 1 ket minus is equal to 0. This is what I demand. Now I make the multiplication. I make use of the orthogonality. The only non-zero combination of bra plus here is with ket plus. Right? The combination bra plus ket minus is 0 because these are orthogonal. Similarly, the combination bra minus ket plus is 0 and bra minus ket minus is 1. Okay, this means that I can take the multiplication, I can take the first term, and the only non-zero combination here is A star A, right? Sorry, A star from here and 1 by root 2 from here, A star divided by root 2, bracket plus plus, which is 1, plus, okay, the other combination A star bra plus bra minus, okay, ket minus, okay, bra plus ket minus, that's 0, orthogonality, okay, plus B star divided by root 2 e raised to I delta 1 is equal to 0. Okay, this means, okay, this equation actually means I can write B star divided by root 2 e raised to I delta 1 is equal to minus A star divided by square root of 2. I can cancel the square root of 2 here, and I get what I see is that from here, okay, I can also multiply by e raised to minus I delta 1 on both sides, so I get this thing. B star is equal to minus A star e raised to minus I delta 1. Right? This is what I get from the orthogonality condition. Okay, so let me just write it down. I get a relation between A and B. of this form. All right. So what I get is B star is equal to minus A star e raised to minus I delta 1. This means that B is equal to minus A. I'm just taking complex conjugate on both sides. So this is equal to minus A e raised to I delta 1. Okay. Alright. This is fine. Alright. But this doesn't determine it completely. This does not determine it completely. I only have a relation between A and B. Alright. Now how do we determine A and B? Now we can also use the normalization condition. We can demand that bracket bra Sx minus ket Sx minus is equal to 1. Right? Demanding this means that modulus A square plus modulus B square has to be equal to 1. Alright. But here I already have b in terms of a, so I can write this as modulus a square plus modulus b square, right? Modulus b square can be written as modulus b square is b star or b star b, that's equal to minus modulus a square. So there's a minus here, so it's plus modulus a square, and this phase factor disappears. All right, plus this is modulus of a square is equal to 1, or twice modulus of a square is equal to 1. Modulus of a square is equal to 1 by 2, or modulus of a is equal to 1 by root 2. We can write a is equal to 1 by root 2. Okay, here again I have made a choice. Okay, again I have made a choice. In principle, there could be a phase factor here of the form e raised to I5. Right? But I can choose the first coefficient. Okay, using the freedom that we talked about earlier, I can choose the first coefficient to be positive and real. Right? So using that freedom, I choose a equal to 1 by root 2. Now, if a is equal to 1 by root 2, then b is equal to minus a e raised to I delta 1. Okay. So this is equal to, I have found a is equal to 1 by root 2. So this is equal to minus 1 by root 2 e raised to I delta 1. Right. So I have got a and b. I have got a and b, which means that I can write sx minus as a ket plus a is 1 by root 2, 1 by root 2 ket plus minus 1 by root 2 e raised to I delta 1. Why? Because b is equal to minus 1 by root 2 e raised to I delta 1. Okay. And ket minus. Right? This is what I have here. Now, what we have done so far is that we have just found ket Sx plus and ket Sx minus. And what did we do to find ket Sx plus and ket Sx minus? We looked at the experimentally measured probabilities and then used the theoretically predicted probabilities, equated them, and then we used some freedom to write ket Sx plus like this and ket Sx minus in this form. All right. Okay. Now the next thing we can do is that, all right, we can actually find this delta 1. That we can fix this delta 1 also. That we'll do quite soon. All right. And now the next thing what we need to do is we need to find the operators Sx and Sy. I think we already did operator Sz. Right? We can also find operators Sx and Sy. Okay. So that's what we'll be doing next. To summarize, we have got Sx plus is equal to 1 by root 2 ket plus 1 by root 2 e raised to I delta 1 ket minus. All right. And using the orthogonality relation, using the orthogonality requirement, we see that we can write Sx minus, ket Sx minus as 1 by root 2 ket plus minus 1 by root 2 e raised to I delta 1 ket minus. Okay, where we have again chosen the coefficient of ket plus to be real and positive by convention. All right.